Hello, 7th graders. This is Miss White, and today we're doing lesson 14, converting rational numbers to decimals using long division. Now in this lesson, you will need a calculator to complete it. So go ahead and pause this video if you may need to get a calculator. Let's start example 1. Can all rational numbers be written as decimals? Using the division button on your calculator, explore various quotients of integers 1 through 11. Record your fraction representations and their corresponding decimal representations in the space below. So let's go ahead and do some examples. The first example I'm going to do is 1/2. Go ahead and type into your calculator 1 divided by 2. Great. The answer you should have got was 0.5. Now let's do the next one, 1/3. Type in 1 divided by 3 on your calculator. All right, the answer you should have got was 0.33 repeating. What about 1/4? Go ahead and type 1 divided by 4 on your calculator. The answer you should have is 0.25. Let's do 1/5. Type into your calculator 1 divided by 5. The answer you should have got is 0.2. Let's do 1/6. Type in 1 divided by 6 in your calculator. The answer you should have got is 0.166 repeating. Let's come over here and do 1/7. Type in 1 divided by 7 on your calculator. Now this answer is a little different compared to most that we've had. We come up with 0.1428. I realize there are numbers to follow that, but we will just stop there. Let's do 1/8. Type in 1 divided by 8. And your answer should be 0.125. Let's do 1/9. 1 divided by 9 into your calculator. And that gives us 0.111 repeating. Let's do 1/10. When we take 1 divided by 10 and type it into our calculator, we'll get 0.1. And then finally, the last one, we have 1/11. So 1 divided by 11 typed into your calculator gives us 0.090909 repeating. When typing into your calculator, what two types of decimals do you see? When some decimals stop, and some fill up the calculator screen. Sorry guys, that's my dog. What this proves to us is that all rational numbers can be represented in the form of a decimal. We have seen already that fractions with powers of 10 in their denominators can be represented as terminating decimals. Therefore, other fractions must be represented by decimals that do not terminate. Also, let's keep in mind that we did not have any quotients of integers that couldn't be represented as decimals, and that's because dividing by 0 is not allowed. All quotients have decimal representations, but some do not end. Example 2, decimal representations of rational numbers. In the chart below, organize the fractions and their corresponding decimal representations listed in example 1 according to their type of decimal. On the left side of our chart, we're going to have terminating. And on the right side, we're going to have non-terminating. Now let's go through our decimals from example 1 and categorize them whether they are terminating or non-terminating. So let's look at 1/2 equals 0.5. Because the decimal stops, or you could say it ends, that's going to be in our terminating column. So 1/2 equals 0.5 is in our terminating column. Let's look at 1/3. 1/3 equals 0.33 repeating. Because it repeats itself, it's going to go in the non-terminating column. So 1/3 equals 0.333333 and so on. Let's look at 1/4. 1/4 equals 0.25. Because our decimal stopped and it did not go on forever, 1/4 equals 0.25. Let's look at 1/5. 1/5 equals 0.2. Because the decimal does not go on forever, 1/5 equals 0.2 is in our terminating column. 1/6 equals 0.166 repeating. Because the decimal goes on, it is in the non-terminating column. So 1/6 equals 0.16666 and so on. What about 1/7? When we typed that 1 into our calculator, we got 0.1428, but the decimals kept going. So that's going to be in our non-terminating column. So 1/7 equals 0.1428 and so on. Let's look at 1/8. 1/8 equals 0.125. Our decimal stopped there, so that is in the terminating column. So we have 1/8 equals 0.125. For 1/9 equals 0.1 repeating. Because it repeats, that means it does not end, and so it is non-terminating. 1/9 equals 0.111111 and so on. Now, let's look at 1/10. 1/10 equals 0.1. Our decimal ends, so that's going to go into the terminating column. So we have 1/10 equals 0.1. And then finally, we have 1/11. 1/11 equals 0.090909 and so on. So because the decimal keeps going, it's going to be in our non-terminating column. So 1/11 equals 0.090909 and so on. All right, let's go to our next page. Example 3, converting rational numbers to decimals using long division. Use the long division algorithm to find the decimal value of -3/4. Now first, let's remember when we have to divide this first. So let's set this up as a division problem. We have 3 divided by 4. Now, when we do this problem, we know that 4 cannot go into 3 once, So then we look and add our 0 and say how many times can 4 go into 30? Well, 4 can go into 37 times. Because it's passive decimal, we need to put the decimal on top. 4 goes into 37 times. 7 times 4 is 28. And 30 minus 28 gives us 2. Now let's bring down the 0. How many times does 4 go into 20? And that is 5 times. 20 minus 20 gives us 0. So we are done solving then. But what we didn't do was add our negative value, and now we need to add it to what we solved for. All right, so our value that we got was 0.75, and now we need to make that value negative. So now we have negative 0.75. Use the example above to help you complete exercise 1. Convert each rational number to its decimal form using long division. Please make sure that you use the correct steps. Please pause the video and check your answers after. For A, your answer should be negative 0.875. Remember, because there was a negative in front of the fraction, you needed to add your negative value at the end after you were done dividing. Then for B, because there was no negative number in front of our fraction, we didn't need to change it back to a negative. It's just positive. Let's go ahead and move on to the next page. Example 4, converting rational numbers to decimals using long division. Use long division to find the decimal representation of 1 over 3. Let's go ahead and solve 1 over 3. So our numerator is going to go inside, and our 3 is going to go on the outside. Now, how many times did 3 go into 1? Well, 3 doesn't go into 1. So we are going to put a 0 on top. Now that we're adding a 0, we know that this is going to be a decimal here, and so we need to add our decimals for the rest of our long division problem. We're going to add a 0 on the inside and say, how many times does 3 go into 10? Well, 3 goes into 10 3 times. 3 times 3 is 9. So we are going to subtract the 9 from the 10. So 10 minus 9 gives us 1. Now we're going to add another 0, and we're going to bring it down to make our value that we need 10. So 3 goes into 10 3 times. 3 times 3 is 9. And we're going to take 10 minus 9 gives us 1. We're going to add another 0. Bring down our 0 to make our value 10. How many times does 3 go into 10? 3 times. 3 times 3 is 9. We're going to subtract 9 from 10. 10 minus 9 gives us 1. Now we could keep going on, but the remainders repeat, yielding the same dividend remainder in each step. This repeating remainder causes the number in the quotient to repeat as well, as we can see up here. Because of this pattern, the decimal will go on forever, so we cannot write the exact quotient. We cannot possibly write the exact value of the decimal because it has an infinite number of decimal places. Instead, we can indicate that the decimal has a repeating pattern by placing a bar over the shortest sequence of repeating digits, called the repeatant. So, for example, we see that we have 0.333 here. What we could do is write it as equals 0.3 repeating with the bar over. When a remainder repeats, the calculations that follow must also repeat in a clinical pattern, causing the digits in the quotient to also repeat in a clinical pattern. Circle the repeating remainders. So those repeating remainders would be 1, 1, and 1. Exercise 2. Calculate the decimal values of fractions below using long division. Express your answer using bars over the shortest sequence of repeating digits. What I would like you to do is look at example 4 above and do the same things for these problems. What you will notice is that all of these fractions will have a repeating decimal. Let's do A together. We have 4 divided by 9. How many times does 9 go into 4? Well, it goes in 0 times. Now we're going to add our decimal to the top and in our box. Let's add a 0. How many times does 9 go into 40? 9 goes into 40 4 times. 9 times 4 gives us 36. 40 minus 36 gives us 4. Let's go ahead, add another 0, bring our 0 down to make our value 40. And how many times does 9 go into 40? 4 times. 4 times 9 is 36. 40 minus 36 is 4. Again, we're going to add a 0, bring down our 0 to make our value 40. How many times does 9 go into 40? And that is 4 times. 9 times 4 is 36. And we still get a remainder of 4. I want you to go ahead and circle your remainders. Great. Now we understand because when there's repeating remainders, that means that our decimal is also going to be repeating at the top. So, for example, now we know that negative 4 over 9 equals negative 0.4444 and so on. And the way that we're going to write that is negative 0.4 repeating. That way we don't have to write an infinite amount of number of 4s. Go ahead and pause the video to complete B. Then play the video to check your answers. Alright, after a long division problem, we see that our answer is 0.090900909. But when we come back over here, remember we had to add our negative from our fraction. So we have negative 0.090909. To simplify that down, we have negative 0.09 repeating. Remember, because the 0 and the 9 repeat, we have to make sure to put the bar over both of those numbers. Also, let's look at the pattern over here with how we come up with the same remainder every time. The only reason why the remainder is 1 down here is because if we were going to add another 0, it would be 10 again. Alright, so the summary for a lesson is real world requires that we represent rational numbers in different ways depending on the context of a situation. All rational numbers can be represented as either terminating decimals or repeating decimals using the long division algorithm. We represent repeating decimals by placing a bar over the shortest sequence of repeating digits. All right, great job today, 7th graders. I will see you in class.